Hello. So we'll wait for some time. So it's almost 3 o'clock. We'll wait for some time for people to join. Meanwhile, can one of you update me till what part professor has taught you? You can type in the box if you want. So we'll just wait for some 2-3 minutes if somebody else wants to join. And meanwhile, if someone can update me till what part professor has taught you in last class, that will be very great. Anyone? Anyone of you? I am audible, right? Yeah, so can one of you update me where professor ended the last class? Like he started Boolean or ended at properties of Boolean algebra? Before minimization, okay. So sum of product and product of sum has been taught. Okay, K-maps, fine. Okay guys, so I think we should start the session now. So if somebody is still joining, that is fine. We'll update them a bit. So last week, as I took feedback from you guys, so you guys wanted to solve more number of problems in these sessions. So last time we had a bit of less number of problems. So this since after beginning with this class, I will be focusing more on the problem solving part. So I am Presh Padwaje and welcome to the second live session of this course, Digital Circuits, which is taught by Professor Shantanu Chattopadhyay. And this week we will be solving questions based upon number system and Boolean algebra. So Boolean algebra I have covered till introduction in this one, but definitely we'll solve more problems in coming time. So last time we covered a bit on introduction and some basic problems on number systems and why we use them. And this week you guys have finished till combinational functional minimization. So KMF has been started. And this week I will be covering problems based till Boolean algebra. So yeah, the problems that we'll be dealing with in this session will be based on the representation of negative numbers. So as you guys will be aware that there are three basic types in which negative numbers can be represented in these binary form. So there can be a signed representation, there can be one's complement, and there can be a two's complement. So So, just a question to you guys. So, suppose if I have 4 bits to work with, so how many bits can I really use in when I'm using signed representation? So suppose if I'm having 4 bits, how many are actually usable? You can type in the chat box. 3, yeah, correct. So that is pretty straightforward. So in case if we have 4 bits, so this first bit will be used for sign. Then in case, whereas in one's complement and two's complement, all the 4 will be used for representing the number, and but in sign representation, the first one will decide whether your number is positive or negative. So I hope you guys have paid attention while Professor was discussing this topic. Uh, Coming forward to that, hardware conversion is that possible for our these negative number representation. So that was also, I think, discussed to some extent in the classes. But and yeah, since you guys are now aware with gates and what kind of gates we have, so yeah, conversion is possible. So can you tell me in the chat box which gate can we use to convert a positive binary number? Suppose we have these 4 bits directly to its ones complement, ones complement form. So you guys might be aware of this. So just a quick answer. NOT gate, yeah, yeah, true. So NOT gate or an inverter is denoted by this sign. So whatever input you give to it, it will give the output to be opposite of it. So one's complement is nothing but flipping of the bits. So that is very well done by using this NOT gate directly. Then I will touch upon some problems based on floating point representations. So yeah, this can be a bit hectic mathematically, but we'll try to cover it in this session. And then finally, I will discuss some introductory problems on Boolean algebra. So yeah, let's directly get into problems. Floating point representation, please explain. Okay, so before I start this session, let me just revise a bit on floating point. So I'll just clear up this space. Yeah, so floating point representation. So I will try to discuss what the professor has already discussed in the class. So we will go with a standard 14-bit floating point number representation. So FPC is for floating point calculations, but yeah, this is basically floating point number. So yeah, a floating point number would be having 3 components, as you guys might be aware. So can you quickly type in chat box what these 3 components are while I write it in the slide? So the first bit will be for sign, middle part will be for exponents, the final part would just denote the number. So the actual number is stored here. Yeah. So that is sign, exponent, and significant. So this number, which is actually stored here, that is also called as significant. True. So what happens in a 14-bit notation? We use this 1 bit for sign. Then these 5 bits are used for exponent. So I will just write it down here. Remaining 8 bits are used for significant. So I think we can directly explain this using a problem that I've already incorporated in the slide. So we'll directly jump to that. Yeah, so there was this question. So I think this is pretty straightforward since you guys already have told me what are the parts. So you can quickly guess the answer to this question. So that is floating point numbers have following components and what determines the range and precision of the floating point number. So components you guys have already told me. So that is sign, exponent, and significant. So that is already known. But what determines the range and precision? Can you guys point out of these components which defines the range and which defines the precision of the number that you are trying to denote using this floating point number? Yeah, so you guys have guessed the answer to this problem correct. So range is defined by exponent, as Shankha is saying. Anyone else? Precision significant. So yeah, basically Shankha is correct, and if anybody else was guessing the same, so that is right. So range will be defined by your exponent component that comes in center of this notation that professor might have discussed. So this exponent, this basically defines the 2 to power whatever you have the number in exponent part. So this 2 to power will define whatever range you can represent using this floating point notation, whereas this precision is given by the significant part. So yeah, we will get to the floating point notation. So that usually starts with the scientific notation, as we were trying to discuss the floating point representation. So okay, just ignore the problem and the solution part for a bit. So if we have, and let's also consider this to be 28.25 to the base 10. So if I want to write this down in a scientific notation, what would it be? So just quickly type in the chat box. I think this is pretty straightforward, so it will be very easy. If typing power can be problem, you can just mention the number part. You can skip the into 10 to power, whatever the power will be. 2.825. Rest of the people, you are also getting it, or you are just not trying to guess. It will be great if you guys can also try to answer. So if I try to write down this in a scientific notation, that will be 2.825 into 10 to power 10. So this basically goes to significant, but in our floating point notation, what we do is this significant will be this will be denoted as 0.2825 into 10 to power 10. Of course, this is not the floating point notation. This is still in decimal system. So to convert this to your binary system in which you want to represent your number in, we will get to this problem. So
Sir, why 10 to the power 10?
10 to power 10. Okay, so we were trying to represent 28.25, which was in decimal number system. So to represent that, the usual form of scientific notation is you have to give a single digit number at start before the decimal, and the rest of the part goes to the this after decimal point. So if you try to write this in this format, 28.25, so that will come out to be 2.825, and to adjust for this decimal point that you have moved, you have to write 10 to power 10. So if you again convert it back or just solve this multiplication, this will again give 28.25. But yeah,
Sir,
in
we are
our
just
case,
multiplying with 110, na? So it will be only 10 to the power 1.
oh, sorry, my mistake. So yeah, that will be 10 to power 1. Thanks for pointing that out. So yeah, if you want to write this down in scientific notation, that will be 2.825 into 10 to power 1. Correct. So now, if you want to convert this to your floating point notation, so you will have to convert this to binary first of all. So this will be something in binary. So as we have already practiced some problems from previous week, you guys can also parallelly try to convert this directly into binary, 28.25 to the base 10, convert it to the base 2. So I will do it here. Meanwhile, you also try to solve it, and as you get the answers, try to note them down in the chat box. So we'll do this part by part. So first we will solve the left part of decimal, and I'm writing down the remainder to the right side. So I got the part which is before the decimal. Then to convert this, I'll keep on multiplying with 2. So this 28.25, that will turn out to be 11100.10 to the base 2. Now, as you remember from the decimal understanding, whatever we did to convert 28.25 to our scientific notation, we just moved the decimal point one step to the left and wrote that down to power 10 to the power 1 in its multiplication. So if you try to move this decimal point to left side, you will have to multiply this in steps of 2 to powers n. So if you try to write this down in scientific notation, so the usual scientific notation in which there should be a one digit before decimal and rest of the things come after that decimal. So this will turn out to
Sir,
be
why not minus sign consider?
what?
Minus sign, why not consider, sir?
Okay, so that is the beauty of floating point notation. So as you remember, our general form of floating point number is this first bit will be for sign, this second will be for exponent, and the third will be for significant. So since I have a negative number, so if I write down 1 here directly, so whatever is remaining, that is 28.25. So I can directly convert it and try to put it in the remaining boxes. So I just need to figure out now what is significant and what is exponent for this number. So Komali has punched in the answer to be B. Okay, so we will check that. You got it, right? Who was it? Vivekanand.
Yes, sir.
You got it, no? Okay, so moving forward. So as I'm moving the decimal point to left, so I have moved it to 1, 2, 3, 4 steps. So this will be the scientific notation. But as you remember from the floating point notation, the proper value for this will be 0.111001 into 2 to the power 5. So this we need to move one step to left one more time. And this is the notation that will feed into our 14-bit expression. So the first bit will be 1, which is for sign. Then we have exponent. So exponent is 2 to the power 5. So we need to show that 5 is our exponent. So 5 in binary will be simply 00101. So this will be it. But again, as you remember from the excess 16 notation, you guys are aware of excess 16 notation, right? Just a yes or no, a quick yes or no will be fine. Yeah, so excess 16 is nothing, but if you are having 5 bits for your representation of exponents, then whatever is more than 16, that will be added to the power 16 plus, suppose we have some n, and that will be fed into the exponent part. And if something is less than 16, that will signify the negative exponents. So this is to adjust the negative powers of 2, or suppose you need to define a number that is in powers of 10 to the power minus 10 or something. Let's just assume. So if 2 to the power 10 to the power minus 3. So if you try to back convert it, it can be something in 2 to the power minus n. So whatever this minus n is. So to adjust that in this our floating point notation, we use this excess 16 where anything greater than 16 is a positive power and anything lower than 16 is a negative power. So here we have a power of 5 which is positive. So to signify that, we will have to do 16 plus 5 for our notation, that will give out to be 21. And to adjust for that, this will be written as 10101. So our exponent part will be then 10101. And as we have already figured out the significant, that is 111001. So these are 6 bits, so rest of the 2 bits will be simply 0. So if you look at this matches to the option B. Now, these can be a bit tricky because if you just forget to account for excess 16, then you might get an answer C, or C can also you can get, but then you have to remember that you want to express your positive powers and not negative powers. So that is the beauty of floating point notation. So here, negative numbers can be defined, even the negative exponent powers can be defined. So this is just a standard notation that we use.
Sir, may I ask you one question, sir?
Yeah, sure.
Now, I'm telling you one thing that already you're given it minus 28 by 25 into
Yeah.
10 to, okay, 28 I've already converted to binary first. Then for
Yes.
minus, I wanted to do complementary cases with.
No, in this case, this first bit represents sign. So if you directly account for that, so you already have said that your number will be negative.
Okay.
So like
In,
this is different from your sign representation and ones and twos complement also. So this is different from that.
हमको एक जगह पर समझ में नहीं आ रहा है तो 28 को पहले अच्छा उसका बाइनरी करके
हम्म।
तो 110 अच्छा अच्छा ये था 28 का बाइनरी का तो
हाँ,
1100 अच्छा ठीक है तो ठीक है
आपको समझ आया ना?
समझ अच्छा ठीक है
ठीक है, एक बार I will repeat this in short.
हाँ
So whatever process that we did, so
हाँ
first part was look for sign.
हाँ हाँ
So if that is positive or negative, account for that in
हाँ,
first bit. Then whatever you are having, that will be only your number. So in this case, we had only 28.25. So if you have 28.25, convert the remaining to binary.
हाँ दिखा दिए थे तो बाइनरी बस का बचा हाँ
So we did this binary conversion.
हाँ
Then
हाँ
write this down in this significant and exponent notation.
एक्सपोनेंट अच्छा 2 की बात पकड़ने से क्या होगा हमको
So हमारे पास 2 to power 4 था, बट क्योंकि हमें जो होता है सिग्निफिकेंट हमेशा 0 पॉइंट और जो पहला होता है वो 1 होना चाहिए. तो टू एडजस्ट फॉर
अच्छा वो
दैट,
जो अच्छा 2 टू दी पावर 4 कैसे होता है 11010 इंटू दी पावर 4 कैसे हो पहले ऊपर
हाँ
जो था 110100 अच्छा अच्छा तो अपने वो
या तो वो
तो
डेसिमल
2
पॉइंट मैंने मूव किया है 4 स्टेप से.
अच्छा वो डेसिमल को हटा दिया गया
तो वो लेफ्ट मूव हुआ है 4 स्टेप्स एंड देन टू अकाउंट फॉर द सिग्निफिकेंट पार्ट, जैसे इसमें हमें 0.1 सपोज करके लिखना होता है, तो उसके लिए 2 to power 5 अकाउंट हो गया. तो सिग्निफिकेंट प्लस एक्सपोनेंट आई हैव डिफाइंड and then just fill it up in the bit that you have. So this 14-bit notation becomes this. So I hope you guys got this right.
तो समझ नहीं आ रहा अच्छा ठीक है देख लेंगे वो तो
नहीं,
यहाँ पर
you
समझ
can
में
ask.
यहाँ पर तो देखिए सर यहाँ पर
हम्म
तो समझ में नहीं आ रहा है 11010 इंटू दी पावर 4 देखिए ये तो ऊपर जो लिखे थे 20.25 उसको डेसिमल बाइनरी में कन्वर्ट किया था ठीक
हम्म
है तो ये जो है वो क्या है जो यहाँ पर जो है 11010 इंटू 2 टू दी पावर 4 वो उसको
ये
छोड़
भी
के
यही नंबर है. सो ऐसा होता है कि जैसे आपने 28.25 लिखा इंटू 10 टू पावर 0, या फिर
हाँ
2.825 लिखा इंटू 10 टू पावर 1.
अच्छा अच्छा ठीक है
So
ये
ये दोनों इक्वल है. तो some issue might be there because the powers are in form of two powers.
अच्छा ठीक
So I think everybody got it right. So if somebody has some doubt, better ask now.
सिग्निफिकेंट रिप्रेजेंट तो नेगेटिव है अच्छा अच्छा उसकी जगह अच्छा ठीक
तो उसका हमने साइन बिट में अकाउंट कर लिया था पहले.
अच्छा साइन तो नेगेटिव अच्छा ये 10101 कैसे आया वो जो 10101 है
तो 101 जो है वो आया बिकॉज ऑफ एक्सेस 16 नोटेशन. सो आई थिंक आपने जब प्रोफेसर ने पढ़ाया था तो उस टाइम पे बताया होगा उन्होंने कि जो हम 5 बिट यूज करते हैं,
अच्छा
दैट इज,
फ्लोटिंग पॉइंट में अच्छा अच्छा फ्लोटिंग पॉइंट में
फ्लोटिंग पॉइंट में, तो जो 2 टू पावर 5 होता है दैट गिव्स आउट टू बी 32. सो वी जस्ट डिवाइडेड बाय 2, और जो उसका मिड पॉइंट होता है we use that as a reference point. So anything greater than 16 will be positive powers and less than 16 will be negative powers. So that is to account for negative exponents. So अगर आपको और precision में define करने numbers तो उसके लिए है. Okay, I hope you got this problem. फ्लोटिंग पॉइंट में और किसी को कुछ डाउट आता है तो प्लीज आस्क. इट इज अ बिट ट्रिकी and that is good to know. So yeah, now we'll start from the first problem that I had kept here. So which of the following might be a kilo in computer memory? So kilo, as you know, would be like 10 to power 3. So that is in decimals. So yeah, just take a guess for this question. You guys already know how a computer works, what number system a computer follows.
किलो मतलब किलो बाइट को
D.
बोलते हैं, किलो
Not
बाइट।
kilobyte, just kilo. So like kilo,
D,
giga,
sir. Answer D.
what?
D.
B. Okay. Komali is saying C. You guys can type it down. So this is, I think, pretty straightforward. So Ravi says D. Okay. So Ravi, this kilo is in 10 to power 3. That is already like we know because it's in our counting system. But you guys would remember what a computer works in which number system it works in. Tanushree says C. Okay. Okay, so Project also says C. So okay, yeah. Pretty much C is the answer. So
2
why
raised
is
to
that?
10.
Yes, Ravi.
2 raised to 10.
2 raised to 10. Yeah, yeah. True. Correct. So if you see this 1000, the nearest power of 2 that can represent 1000. So that will be 2 to power 10. That gives out to be 1024. So in computer number system, you cannot always say that yeah, kilo and these all will be exact numbers, but computer just approximates. So since the number system is different, so 1000 can easily be defined in 1024 steps. So that's why for a computer, a kilo is given by 2 to power 10. And why only 2? Because computer works in binary. So even 16 to power 3 would be something in thousands. So this can also be okay, but a computer has to work in binary. So the answer would be C for this. Now this is a relatively simple question related to binary numbers. So can you guys perform this multiplication and quickly type in the answer for this? Meanwhile, I will solve it here. And yeah, if you guys are done asking, please try to mute back your mics. It adds to noise a bit. So let's start with this. We have 1001 into 1100. So as you guys would be aware, how a multiplication works is that you have to multiply the whole number one by a bit. So we will start by multiplying with 0. So if you multiply 0 to this number, this will be 000. Then you have to move a step to the left and then again multiply the next bit to our the number which is at top. That will again give 0000. Then comes the turn of this third number. So this will give out 1001 and again moving one step left.
110
So sorry. Yeah. And the rest of the
C.
numbers become don't care situations. So that is equivalent to 0 in our case. And then just do the addition to complete this multiplication. So the number you will get will be
सी होगा सर, सी
11011000.
हो जाएगा, सी हो जाएगा
C.
ये सी।
Yeah, yeah, true. So answer for this problem will be C. So I hope everybody got this. So that's why keep in typing the answers as you solve the questions. So that I know that I'm going at a comfortable pace. Shankar is saying, can we convert to decimal and then multiply? So Shankar, for smaller numbers it is okay. Like this, these are only 4-bit numbers. But let's suppose today's computer work in 64-bit, 32-bit. So you won't try to convert that and then multiply. So for computers, that conversion is not an option. You can do it, but after a certain threshold, you should just try to do it in binary. That is way easier. Yeah, so I think this was also covered in number system, changing the bases, and also we practiced, I think, at using base 3 in our last session. So this is not base 3, but relatively simple. So just change the base of this number, that is 2.7645 to base 2. So already in this floating point calculations, you guys have seen how we do it quickly. So you guys can try to solve it. Meanwhile, I will solve it in here in the slide. So, like again, just as we did earlier, I will take the part which is before decimal and convert it. So this will require division, and the part which is after this decimal, that will require multiplication by 2. So this division, as we go on performing, this will give out 10 for 2. Then the decimal point is encountered. Then we simply multiply it, and as we get a whole number out of this fraction, that we try to write it down on the right. So as I encountered a 1, this will just go to left. Okay, people have started to type in answers. Good. Then ignore this number and again multiply by 2. So this, after you take it out, just write it down to be 0. Then again multiply.
सर ये डी हो जाएगा,
D.
देखिए यहाँ
Ha,
से
yeah,
साफ आ जाता है
yeah, true.
और स्टेप का जरूरत है, डी हो जाएगा.
And as you notice, this fraction you cannot write it down completely. So that will just keep on going multiplying. So like in floating point, as you remember, the significant is 8-bit. So here also you have to define an extent till which you want to precisely define your number. So this is just dot dot dot, but computer won't consider this. It will, I think, it can truncate it here or here according to the type of operation that the computer would be doing. So the answer to this question will be D. I hope everybody got this answer. So some of the people got B. I hope you guys got the correct answer again.
सो ये करना इजी है पूरा, क्योंकि देखिए पहले तो 2 का बाइनरी करने से हमको पता ही चल गया ए और सी
हाँ,
नहीं होगा, हमको चाहिए
yeah.
कि बी और डी होगा. उसके बाद दो मल्टीप्लिकेशन करने से हमको पता चल गया कि ये कौन होगा, मतलब बी और डी.
Yeah,
बस.
true, true. So, like elimination of the options, that is also one way to go. So that's good. Then again, based on conversions, so last time we did a less number of conversions. So try to convert this number, which is given in decimal, to octal and its hexadecimal counterpart. So again, I will solve this parallelly with you guys, and rest of you who are getting the answers quicker, you can type in the answer. So here again, based on the base that we have, I will take the part which is before decimal and divide it by the base that I'm trying to convert to. So in first case, I'm trying to convert this to octal number system. So I will divide it by 8. And the remainder I will write down here. So for octal, I'm getting 16 point something. So again, if you try to eliminate, here A and D gets eliminated. Okay, I think pretty much every other option gets eliminated, but I would just say solve it. Yeah, people are still joining. Okay, guys, try to join on time. That is okay if you join at any time. That is not an issue, but still. So this becomes 0 again. So yeah, pretty much it will be something 16.47 in our octal. Now trying to convert this into hexadecimal. Similarly, I will use, since we need to convert to base 16, so I will divide this number by 16 and divide the number which is left to the decimal by 16 and multiply by 16, which is to the right of this decimal. So if I divide this, so this will be pretty much directly 14, and 14 will represent by E in hexadecimal. So this becomes E point something 0.6125. You have to keep multiplying by 16 till whatever precision you need. A is the answer. With got A. I hope you didn't get A. Try to solve it again. So here 9 will come and the remaining 0.830, that will again be multiplied with 16. Something 12 point something will come. So this 12 will convert out to be, okay, just simply use calculator if this gets hectic. So rest of the people are not getting the answer or what? So just try to punch in the answer. I hope this is lengthy, but you have to practice it. So this will be something 13.28. So 13, if you convert it to hex, okay, I think there is some mistake in the options. So that is actually E.9. Actually, it will come out to ED. Did someone calculate the hexadecimal part? If you are getting something, try to punch it down. I think there is a, I think I wrote down the option to be wrong. But yeah, let's correct it. So whoever is getting the correct answer, type it down. This is actually 0. Yeah, so answer is B. But yeah, whatever value you are getting in the hex part, type it down.
Hello, sir.
Yeah, yeah, Ravi, tell me.
Sir, if we convert this into binary
Hmm.
and then we convert it into octal and hex, then
Yeah, so
Uh,
that is
you,
also correct method. So
now, current
last,
method means we will feel easier. It's easier to solve also because if we convert it to binary, it will
hmm,
be easier for any user to solve.
yeah, yeah, true. So last week we went that way. So this is mathematically intensive, but still, like, this is these two bases are in such way that you can directly convert from binary. But what if the base were different? So in last week, like we solved using base 3. So yeah, it is a bit mathematically intensive, but you have to practice that and you have to know. So what you need to do. So the takeaway from this question is before the binary this decimal is encountered, divide it by the base, and after the decimal point, keep multiplying with by the base and keep writing down the whole number that you encounter. So if you follow that, you will get the answer to be B in this question. And I think yeah, most of the people are getting B. Now we'll move on to the next question. So yeah, solve this problem using 1's complement. So this is based on the Boolean, this negative notation that you guys would have learned this week. So those who are able to solve it, you solve it and type in the answer. Meanwhile, I will solve this question on this board. So we have two numbers, 7 minus 13. Can you please mute Ravi? Who else is unmuted? So try to mute once you are done asking your doubt. Okay, so 7 we will convert to binary. So if you convert 7 to binary, this will be 0, 111. And since 7 is already positive, so you don't need to find its ones complement. Yeah, for this complement based subtraction, what we have to do is we have to write down 7 in binary in ones complement form, negative of 13 in binary in ones complement form.
See,
Yeah, Ravi. You are saying something? Okay, guys, try to mute your mic after you're done. So 13. Firstly, we will write down the binary equivalent of positive of 13. So that will be 1101. So this represents 13. And when you try to write down negative 13, you can directly complement it. So complementing this will directly give 0010. And this will represent minus 13. Another operation that you need to do will be 7 plus minus 13. So if you write these two numbers down, you need to actually add it now. So addition basic rules you already remember. So this becomes 1001 in binary. But again, this is a ones complement form. So this will be, if you try to directly see from decimal also, this will give out to be minus 6. So we are getting this answer just to back check because these are a less number of bits. This we can try to back check, and this 6 is actually 0110 and negative of 6 will be 1001. So here A will be the answer. So yeah, I think Shankha got the answer. Rest of the guys, I hope you guys are also solving this. So you guys got the answer or what? Just try to type in the answer or
Sir,
yeah, yeah,
I'm
Janta.
getting you. Okay, okay. As it is minus 6, that's why it represented as 1001. Okay,
Okay.
minus 6 है इसके लिए.
Hmm. So
इसके
that is
लिए
just to check if the number of bits are less. If the number of bits are more, so whatever number you are getting after this operation, that will be the answer. In case of this one's complement. You got it? Let's try to do the inverse problem of it. Let's try to solve 13
yes.
minus 7. This is also very straightforward. So 13 we have already calculated, plus 13 is 1101. 7 is actually 0111 and minus 7 will be 1000. That will be minus 7. So if you add this, okay, I think this is not the correct example, but I hope you got the thing that how to do this subtraction, right? You got it, right? Okay, moving on to next problem.
Repeat again.
What we done? Hello?
Sir, repeat again, sir.
This subtraction. Okay. So we need to calculate 7 minus 13. These are in base 10 using 1's complement. So 1's complement, we need to convert these numbers to binary. So 7 base decimal would become 0, 111 in binary, and 13 would become 1101 in binary. But since this is a negative of 13, so 1's complement will be simply flipping the bits. So this will become minus 13. So now you need to add these two numbers. So 7 minus 13 would become this addition you have to do simply 1001, and this will be in 1's complement form. And if you try to just check this problem, whatever you got, so 7 minus 13 in decimal, you know directly gives minus 6. And we just back checked it by converting by writing down the 1's complement of 6. That gives out the flipping of bits of 0010, and it becomes 1001. So that is the answer that we got. So yeah, you know that the answer that you got is correct. So since this is a very small problem, this is only remaining till 4 bit, that we can quickly check. So that will give out to be A as our answer. My voice is not audible. Still the problem is there. Hello?
Yes, sir.
Yeah, you got it right.
Yes, sir.
Okay. So now my voice is clear, right? So I think Mala raised a concern that voice is not audible.
Sir, answer B is wrong, na sir.
Yeah, B
So
will
we
be
have
wrong. Yeah, tell me.
why? Because if you will not getting carry, again we have to convert in one's complement. We should not
Uh,
follow that rule for one's complement subtraction, sir.
Sorry, didn't get you.
Actually, in one's complement subtraction, there is a rule. If we didn't
Hmm.
get the carry, the result is in one's complement form.
Yeah,
If you get carry, we have to add the carry to the MSB if we get the carry. So that is the rule for the one's complement subtraction.
yeah. So here in
But
this case, we don't get a
uh,
carry, right?
okay, so that's why directly write that answer 1001.
Yeah. And
Okay, sir.
just
So
since
I'm
this
a
is
little bit confused. Okay.
no, that's fine. So actually, this we are only discussing the problem, so that is also on my part. So I'm
Okay,
assuming
sir.
that
Thank you.
you guys have went through the lectures.
Okay, thank you, sir.
Yeah. Now moving on to the next question. Now this is pretty straightforward. So try to take a guess for this. So what is the range of numbers representable by sign and 2's complement using 8 bits of binary numbers? So I will just write down the ranges that are defined by different representations. Not audible. Mal, I think there might be some issue at your end. So try to reconnect. So the ranges for these representations are given by 2 to power n minus 1 from negative side to 2 to power n minus 1 to positive side. The same is for 1's complement. Just in case of 2's complement, this becomes 2 to power n minus 1 to 2 to power n minus 1 of minus 1 to positive side. So yeah, the answer is option D, Shankar. Yeah, yeah. So if you remember these things, that is pretty much true. Or else the thing that is common in signed and 1's complement is that we actually have plus 0 and minus 0. So 2's complement will be always having a one greater number to represent in negative part. So that is quite clearly seen because here the range of your 2's complement extends from minus 128 to 127, whereas for sine it remains from minus 127 to 127. So just keep a note of these ranges. Now moving on, yeah, you guys are already aware with gates and a bit of Boolean logic. So which of these gate or hardware can be used to find one's complement of a 4-bit binary number? I think you guys are already aware of AND, OR and NOT gates. B. Yeah, Shankar, true. So as in initial part also I
हाँ
discussed.
4 बीट देखिए सर यहाँ पर वो एक पूरा साफ साफ नजर आ रहा है देखिए 4 बीट बाइनरी नंबर जो बोल रहे हैं बाइनरी मतलब देखिए यहाँ
हम्म
पर सब कुछ है जीरो नहीं तो वन यहाँ पर
हम्म
सिर्फ नॉट से क्या हो जाएगा नॉट में मतलब वन जो है उसका वन जो है वो जीरो हो जाएगा
जीरो देगा,
जीरो
हाँ
वन हो
करेक्ट।
जाएगा इसका मतलब
हम्म
वन कॉम्प्लीमेंट में भी वैसा ही है अगर जीरो 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 चार चार तो जीरो बैठेंगे तो नॉट दे
हम्म
देंगे तो नॉट देने से क्या होगा चार तो वन हो जाएगा वन जीरो वन जीरो जीरो वन जीरो वन हो जाएगा
ट्रू
यही है
ट्रू ट्रू।
यही है सबसे मतलब ये पूरा साफ ही आता है पूरा इसमें
हाँ ये स्ट्रेट फॉरवर्ड क्वेश्चन है। तो just basics of gate should be known, so that's why I put this here. And moving on to next question. Now you have to find 22 minus 31 which are in base 10 using 2's complement. So you guys start to solve it parallelly. I will also try to solve it on this board. So let's first convert this to binary. So 22 to the base 10 would give out. I'm just performing the division. So yeah, so you will get 10110. That is in binary. And for 31, you will be getting 11111. But you have to take a note that this is a negative of 31, so this 22 of 10 minus 31 of 10 can actually be written as 22 of 10 plus minus of 31 in 10. So this minus of 31 you have to represent using 2's complement. So how 2's complement is found out is by flipping the bits.
मतलब सबको देखिए वन एस कॉम्प्लीमेंट पहले कर दीजिए पहले वन
हाँ
एस कॉम्प्लीमेंट करना पड़ता है
हम्म
उसके बाद उसके साथ प्लस वन कर देना पड़ता है
हाँ true. So 00000
हाँ
and
उसके
after
प्लस
flipping
वन
that 00001. So
हाँ
this is minus 31 in 2's complement.
उसके बाद ऐड कर दीजिए
And
दोनों
now we will do the addition. Yeah. तो आपने आपने सॉल्व कर लिया होगा ना आपका आंसर क्या आ रहा है?
मैंने एक्चुअली वन 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 जीरो वन
11101.
हाँ इसमें से कोई तो मैच ही नहीं कर रहा है ओ अच्छा अच्छा ये एक तो फिर से तो ऐड हो जाएगा उससे देखिए एक बार ये मालूम नहीं ये तो इतना ही
Yeah, so
सर
इसमें
एक
ऐसा
जो 5 फीट का जो एक है ना वो डिस्कार्ड हो जाएगा डिस्कार्ड करके वहां पर एडिशन हो जाएगा 5 फीट का जो एक है हाँ हाँ
ट्रू।
इसको
तो जो आपका जो
इसको
आगे
साथ
का
उसको
कैरी है वो आप
ये
डिस्कार्ड
इसको
कर
फिर से
दोगे।
एडिशन कर हाँ डिस्कार्ड कर इसको फिर से एडिशन करना पड़ेगा
आई डोंट थिंक एडिशन करना पड़ेगा।
हाँ देखिए पूरा एडिशन
Sir, we can discard the MSB only if there is a carry. Here to no carry is produced. So how can we discard it?
कुछ कॉम्प्लीमेंट करना पड़ेगा क्या?
हम्म
कॉम्प्लीमेंट इसको फिर सबको लग रहा है कॉम्प्लीमेंट ही करना पड़ेगा।
या सो क्योंकि फिर से हमारे जो नंबर्स है काफी छोटे हैं, तो यू कैन जस्ट ट्राई टू ट्रैक बैक योर ऑप्शंस, सो व्हाट यू शुड बी गेटिंग इन टूज कॉम्प्लीमेंट। सो छोटे नंबर्स देने का वही इसमें ऑब्जेक्टिव है कि इवन इफ यू फॉरगेट सम बेसिक रूल्स which can definitely happen sometimes, you can always backtrack. So 22 minus 31, what is that? It should be giving minus 9, right? Correct. So this is 9. Sorry. So this is 9. If you convert it to 2's complement, 0 1 1 0, and then you have to add 1, you will get 0 1 1 1. So see, so even if you forget that, you have to discard this carry. छोटे नंबर्स के लिए यू कैन डू इट। सो ऑलवेज अगर तुम कहीं पे स्टक भी हो जाते हो, ट्राई टू अप्लाई द सेम रूल ऑन स्मॉलर नंबर्स सो दैट यू रिमेंबर व्हाट इज देयर। सो बिकॉज इसमें इतने रूल्स आते हैं, इतने प्रॉपर्टीज आती है, इट्स वेरी डिफिकल्ट टू ऑलवेज मेमोराइज दैट थिंग। सो यू गाइस गेट इट राइट। सो दिस द आंसर यू विल गेट इन टूज कॉम्प्लीमेंट विल बी सी, 0 1 1 1 to the base 2. I hope you got it right. ये हमारा आंसर विल बी सी। Now moving on. Okay, I think this is the same problem. Then this we have already solved. So yeah, floating point is a big part of this week's studies. So floating point, I hope to everybody floating point is clear. If anybody is having any doubt in floating point, that we can discuss now, because I think we are running out of time. So instead of solving a newer question, if somebody is having a doubt in floating point, you guys can ask. I will try to address to them. If anybody is having something on floating point, you can ask. Then this is again a similar kind of problem that we earlier discussed. So just quickly try to guess which will be the answer. Single precision floating point. Okay, Komali is asking single precision floating point. So yeah, try to guess the correct answer for this. I think this is pretty straightforward. So meanwhile, Komali, what happens is, okay, which is saying A. Yeah, correct. This is the correct notation. And this we have discussed to a bit to extent in that problem. So what happens in single precision and double precision? These are two kinds of floating point representations. So here the number of bits that you try to define the precision. So earlier we have discussed. So this first one is for sign. This is for exponent, and this is for significant. So your precision depends on the exponent value to which decimal accuracy you can represent your number to. So single and double are just two different kinds of representational entities in which double will be having more number of exponent bits as compared to single. So here the difference lies in exponent bits. So you can let's suppose if your single precision is able to go till 10 to power 8 or 10 to power minus 8. So your double will be able to having a range that will be approximately double to this. So single and double are basically these two different kind of floating point representations in which the amount of precision that you get from the notation is different, and that boils down to the exponent number of exponent bits that you have. Number of bits define precision. I hope you got it. Okay, so I think it's already 4 o'clock. How many we have left? Okay, so these are part of Boolean. So I will try to fit that in next class. So yeah, this will be the last problem that we'll try to solve. Yeah, so this is a bit of interesting problem. So yeah, solve it. So meanwhile, I will also solve it here. And just tell me the answer that you guys will be getting. So you can type in the chat box or unmute and tell your answer. So one number we have in base 3, that is 1x in base 3. The other number is y2 in base 7. So what will happen? The direct rule is to bring it to a common base. So we will convert it to decimal because that is the straightforward conversion that we know, and that is based on the powers of the base. So here 1 into 3 to power 1 plus x into 3 to power 0 will be in base 10. That will give out 3 plus x. So this is in base 10, whereas this will give y into 7 to power 1 plus 2 into 7 to power 0. That will be in base 10. So with is saying C. I will just say, just cross check it. Shankar is also saying C. Yeah, I will, again, same thing. Cross check your answers. You all are getting C. So this will be 7y plus 2. That will be in base 10. So these are basically equal numbers as given in the problem. X plus 3 will be equal to 7y plus 2. So what you will get is y equal to x plus 1 by 7. Now still do you think there is an answer? So let me tell you, there is no answer from these options, because if you try to get the first value by just let's say we are doing trial and error. So if you put x to be 0, at that point of time you will get y to be 1 by 7. So it is clear that you have to put x in a way that you get y to be an integer. Yeah, Shankar, correct. Now you're getting it correctly. So if you put x equal to 6, at that time you will get y to be 1. So now you might say that yeah, D is the answer. But is it really the answer? Because the x is coming out to be 6, but your base is 3. So is there a possibility that 6 lies in this base 3 number system? So yeah, I will tell you that 6 would not lie in base 3, because in base 3 only 0, 1 and 2 are allowed. So 6 is not allowed there. So even your first solution is not lying into that. So basically there will be no answer in this. So if you blindly go doing, you can get this is an answer, this is an answer. But you will have to check in which number system you want this number to be. So I hope you got the solution to this problem. I think a similar kind of problem is discussed by Professor in his slides. But always keep in mind what base you are working in and what are the limitations of the numbers that you will be getting. So any doubts till this point? I think I will have to wrap up this session till this question. And in next, I will start with Boolean and we will go till whatever professor covers. So I will just wait for some 5 minutes. And if you guys have some doubts or some concerns or suggestions, that you can type it down or you can directly tell me by unmuting. It might seem that yeah, I'm just solving the problem step by step, but you guys have to realize that these steps are necessary, and you might get caught at any point. Like in earlier problem, where we were just trying to discuss what would be the next step after this point. But just a simple check, if even if you forget what you need to do the next step, just try to do it on smaller numbers, and we directly got that. We don't need to be concerned of this carry. We just have to discard it. So these are the kind of shortcuts that you should be always be having on your fingertips, so that even if you get stuck and even if you don't remember a rule, you can still solve that problem. So I hope you guys got to learn something in this session, something useful. I don't hope something new because you should be paying attention in lectures that professor is teaching. Okay, so I would say thanks for joining this session. And if you guys have any doubts or something, you can always write it back to me. This is my mail ID. You can just drop a mail to that, and I will try to get back to you with the solutions or something. Even if you are having some doubts based on the lecture that the professor is giving, that you can ask, because it might be possible that in online format you might not be able to directly ask him. So we are here for that. So you can directly ask us. Yeah. So see you guys next Sunday, 3 to 4 same time.